All right, so welcome to another section of quantitative methods. Please kindly subscribe to the YouTube channel for more content. We want you to be the first to see our content once we upload it. So please kindly subscribe to the YouTube channel. Just kindly click the red subscribe button at the down right corner of your screen, whether you are using a computer or whether you are using a phone or whatever device. Just find the red subscribe button at the down right corner and please subscribe to this channel so that you'll be the first to see our content once we upload it. Okay, thank you very much for subscribing. Now, in this second part of probability distributions, I would like to talk about specific types of probability distributions. But before then, we need to understand certain basic terminologies. Now, let's note that there are what we call random variables. So random variable is simply a numerical description of the outcome of a statistical experiment or a random phenomenon. So, like I said in the previous video, if you invest in shares, okay, the returns that you get on the shares is a random phenomenon. You cannot predict with certainty. So the return on a share is the outcome of a random phenomenon. So it can be deemed as a random variable. Now let's note that there are two types of random variables. The first type is the discrete random variable. The second type is the continuous random variable. So the first type is the discrete random variable. The second type is the continuous random variable. Now, a discrete random variable can take on only specific distinct values, okay? So for instance, if I want to randomly select cars, for instance, if I want to select or if I want to randomly check the number of cars that have an accident on a highway, that the number of cars that will have the accident on the highway, the probability that a certain number of cars will have an accident on a highway, we are talking about a discrete random variable, because a discrete random variable can take on only specified distinct values. So it cannot happen that the number of cars that may have an accident will be 2.5 or even 3 and maybe 3.7, because they are counted. So one of the things you must know is that a discrete variable is counted. So when we say a discrete random variable, it is just a numerical description of a statistical experiment in which that numerical description can only take a specific distinct value, okay? But when we talk about continuous random variable, a continuous random variable can take on any value within an interval. Continuous random variable can take on any value within an interval. Now, a probability distribution for a discrete random variable is mutually exclusive listing of all possible numerical outcomes for that random variable, such that a probability that occurrence is associated with each outcome, okay? So the outcomes are possibly or usually they are mutually exclusive. That means that if one outcome happens, the other cannot happen. For instance, if you want to look at drawing a distribution for tossing a coin repeatedly, the only outcomes that can come from the repetitive tossing of a coin is either it's a head or a tail, and they cannot happen at the same time, okay? Now, for discrete random variables, we can describe it to be discrete if it can only assume specific values. In essence, discrete random variables can be counted, it cannot be measured. When I say it cannot be measured, it means that it doesn't have decimal, okay? when something is measured, it can have decimals. For instance, your weight can be in kilogram, maybe 76.9 kilograms. But for discrete random variables, they cannot have decimals. The variables themselves cannot have decimals. Of course, the probability of attaining those variables definitely will be decimals, but the variables themselves cannot have decimals. Okay. All right. So here, discrete random variables have three major properties. Number one, if you sum all of them, you should get one. Number two, the probability of attaining a certain variable should be greater than or equal to 0. We can't have negatives. Now, when you substitute the random variable into the function, you find out the probability that the probability that the particular value will occur. So there are three major probability distributions. We have the binomial, we have the Poisson, we have the normal distribution. Now, let's note that the binomial and Poisson distributions, they are discrete probability distributions. They are discrete probability distributions. And then the normal distribution is rather a continuous probability distribution. Okay. So let's pick the binomial probability distribution. Now, binomial comes from the word bi, binomial, bi. So it means two, okay? So you can simply think of a binomial distribution as a distribution that shows the probabilities of events where there are only two possible outcomes. So here, binomial distribution is a distribution for events where there are only two possible outcomes, right? Where there can be a probability of a success or a probability of a failure. Now, if I want to find the probability that, let's say, 6 cars that travels on the road engage in an accident, the probability that a car will engage in an accident is a probability of success. Here, I don't want us to think as probability of success as probability of always something that is good, okay? Probability of success simply means the probability that what the researcher wants to achieve. So if I want to know the number, or if I want to find a probability that, let's say, 6 cars or more, the six cars or more have an accident on a road, that probability that a car will have an accident is a probability of success because that is what I want to find. So let's not think of probability of success as always something good. It is what the researcher wants to achieve. Now, these are the characteristics of a binomial distribution. First of all, as I said, from the name binomial, bi, each trial has only two possible outcomes. Whether it is a success in terms of what the researcher wants to achieve, or whether it is a failure, what the researcher does not desire to achieve. Now, the trials are independent of each other. In essence, when one trial occurs, I mean, it doesn't, and when you do one trial, and let's say you have success, it doesn't influence you to have another success in your second trial. You can have a failure in your second trial or whatever. So here, the trials are independent of each other. Now, each trial has the same probability of positive response. Number 4, there are fixed number of trials. Number 5, the random variable is the positive number of positive, there is the number of positive responses. Okay, a random variable is the number of positive responses. So for instance, if I want to find the probability that 6 cars on the road have an accident, it means that the number of cars that have an accident is a random variable. And as I mentioned to you, we can't have 2.5 cars because cars are counted. So in essence, a binomial distribution is an example of a discrete probability distribution. So here we employ a simple formula to solve it. So let's note that find the probability that X occurs, or find the probability that a number of success we are looking for occurs is equal to n combination X, P raised to the power X, Q raised to the power n minus X. Now note that n is the random sample size, X is the number of successes. When a success is defined, where a success is defined as what we are looking for, n minus X is the number of failures. Then P is the probability of success. Obviously, 1 minus P on the other side is the probability of failure. Okay. So let's look at this example. A company wants to expand its production activities and wants to solicit support from 8 senior managers. The probability that a manager supports the decision is 0.6. Find the probability that exactly 3 support the decision. Now, how do we know that this is a binomial scenario? For instance, first of all, there are fixed number of trials because they want to solicit support from 8 managers, so n is fixed. Okay, so there are fixed number of trials. Another way you can also know is that it is just binomial. The outcome is just binomial. It's either they support the decision or they do not support the decision. Okay, it is binomial, whether they support the decision or they do not support the decision. Okay, all right. Now, so here, find the probability that exactly 3 support the decision. So, what the researcher wants to attain, he wants to find out whether 3 support the decision. So, essentially, probability of success, or P, will be equal to probability that they support the decision. So that would be 0.60. Obviously, Q will be 1 minus P, which is 1 minus 0.60. We will have 0.40. Now, find the probability that 3 support the decision. So if 3 support the decision, it means that you have 3 successes, because the probability of success is the probability that they support the decision. So if 3 support the decision, it means that you have 3 successes. Okay. And the number of successes is depicted by X. So X is equal to 3 in the first scenario. So here, per the formula, we have n combination X, P raised to the power X, Q raised to the power n minus X. So here, the probability of success obviously was 0.6. Probability of failure, as I've shown, is 0.4. The number of trials is 8, sorry. And then in this scenario, the number of successes is 3, right? So n combination X, we have 8 combination 3 multiplied by probability of success, which is 0.6, raised to the power X, which where X is 3 already, we've established that. Then we have 0.4, the probability of failure, that's Q, raised to the power n minus X, that is 8 minus 3, right? Okay. Now, once we take our calculators and punch this, we should be able to get the final answer probability. So once you take your calculator and punch it, you realize that 8 combination 3 will be 56, okay? Then 0.6 raised to the power 3 will be 0.01024, and 0.4 raised to the power 5 will be 0.216. So you multiply these 3 terms, you will get 0.1239, okay? Now let's look at the second example, or let's look at the second requirement, sorry. Find the probability that more than 5 support the decision. So here, the number of successes X is more than 5, okay? The number of successes for IIX is more than 5. So it means that since we know that the fixed number of trials is 8, it means that we are looking for more than 5. We are looking for 6 successes or 7 successes or 8 successes. Okay, 8 successes. And we all know that the or here means addition. So we have probability when we have 6 successes plus probability of 7 successes plus probability of 8 successes. So once we do this, we should be able to follow through and get the answer. So when x is 6, we have n combination x, which is 8 combination 6, 0.6 raised to the power x, which is 0.6 raised to the power 6, because the probability of success and failure, they do not change. Then 0.4 is the probability of failure raised to the power n minus x, that is 8 minus 6, that will be 2, all right? So when we follow through that same idea, we can get probability of when x is 7, you get this, and probability that when x is 8, we will get this, okay? So when x is 7, it will be n combination x, which is 8 combination 7, times 0.6 raised to the power x, which is 0.6 raised to the power 7, times 0.4 raised to the power n minus 7, which is 8 minus 7, then we will get 1 here. Then when x is 8, we have n combination x. So the n is 8, the x is 8, so we have 8 combination 8, 0.6 raised to the power x, which is 0.6 raised to the power 8, times 0.4 raised to the power n minus x, which is 8 minus 8, that will be 0. So once we take our calculators and punch them, we should arrive at a final answer of 0.3156. 0.3156. Now, let's take the second example on binomial probability distribution, and then that will be it for this section. Then the next session, we will talk about the Poisson distribution. Then the final session, we will discuss the normal probability distribution. Now let's take this example. The Ghana Revenue Authority reports that there is a 20% chance of self-employed people evading taxes. In a random sample of 6 self-employed people, what is the chance that exactly 6 will evade tax? So here, the number of trials is 6 because we are looking for a random sample of 6 self-employed. So n is equal to 6. Now, exactly 6 will evade tax, okay? And the probability that they will evade tax is 0.20. So since the researcher is looking for the probability that they will evade tax, the probability that they will evade tax is the probability of success. That is what the person wants to find, okay? That's why I mentioned to you that probability of success is not always something good. It simply means the probability of the requirement of the question. So if the question said, what is the chance that exactly 6 will not evade tax? It means that the probability of 0.80, which is kill, will now be the probability of success, okay? The kill, which is the probability of failure here, if the question read like exactly 6 will not evade tax, it means that the researcher wants to find out those who will not evade tax. That means that the probability that they will not evade tax will now become the probability of success. That would have been your P. Okay, so let's have that in mind. All right, now the number of trials is 6, right? Then the probability of success is 0.20. Obviously, the probability of failure will be that is 1 minus P, which is 1 minus 0.20. Then we have 0.80. Okay. Now, for I, the formula is always n combination x, p raised to the power x, q raised to the power n minus x. So when we are looking for exactly 6 will evade tax here, the probability of, the number of successes will be 6, so x equal to 6. And this will give us n, which is 6, so 6 combination 6. P, which is 0.20 raised to the power x, x is 6, then q is 0.80, which is raised to the power n minus, which is 6 minus 6. All right. So essentially, if you punch your calculators, you should get this answer. The II says 4 or fewer. So let's note that random variables, they start from 0. So it means that 4 or fewer, we are talking about probability that 1 will evade tax, or probability that 2. So we are talking about probability that, 0 will evade tax, or probability that 1 will evade tax, or probability that 2 will evade tax, probability that 2 will evade tax, or probability that 3 will evade tax, or probability that 4 will evade tax, because it says 4 or fewer. 4 or fewer. Okay. It says 4 or fewer. 4 or fewer will evade tax. Okay. Now, let's work through the II here. When x is 0, it will be n, which is 6, combination 0, 0, the p, which is 0.2, raised to the power 0. Then the q, which is 0.80 raised to the power 6, because 6 minus 0 is 6. Then for when x is 1, so plus, because of the or, 6 combination 1, 0.20 raised to the power 1, 0.80 raised to the power 6 minus 1 is 5, or it could be 2, which is 6 combination 2, 0.20 raised to the power 2, 0.80 raised to the power 4, or it could be 3, which is 6 combination 3, 0.20 raised to the power 3, 0.80 raised to the power 6 minus 3, which is also 3, or finally, it could be 6 combination 4, that's when the number of successes is 4, 0.20 raised to the power 4, then 0.80 raised to the power 6 minus 4, which is 2. Then when you punch this, you should get your answer. All right, so once you sum it up, you should get around 0.9984. Okay. Once you sum it up, you should get 0.9984. Now, alternatively, if we say 4 or fewer will evade tax, and we know that there are just 6 number of trials, okay, it means that because probabilities sum up to 1, you could have alternatively done for 5 and 6, then subtract the answer from 1. So if we do for 5 and 6, it would have been 1 minus probability for 5 or 6, because probability should sum up to 1. So this will be 1 minus 6 combination 5, 0.20 raised to the power 5, 0.80 raised to the power 6 minus 5, which is 1, plus 6 combination 6, 0.20 raised to the power 6, and 0.80 raised to the power 6 minus 6, which is 0. So essentially you get 1 minus 0.0016, then you get 0.9984, okay? 0.9984, which is essentially similar to the answer we got, okay? So this brings us to the end of our discussions on binomial probability distributions. So this brings us to the end of our discussions on binomial probability distributions. Now, at the end of the series on probability distributions, I'll share the document that I'm using to teach. So please subscribe to our content and find the very last video on probability distributions. That will be on the normal distributions, where I will share this that I'm teaching. I'll share the document on the slides of what I'm teaching. So please kindly subscribe to the YouTube channel for more content. Kindly just click on the red subscribe button at the down right corner for us to bring more content your way. Be the first person to see our content once we upload it. And I would meet you soon on our next video, which features Poisson distribution. Thank you.